Hello, folks. So we're back for what I suspect will be a short little video on just a little bit of tidying for the Sudoku problem that we're working on. It's become a bit of a mess just because I've been writing bits of code all over the place, and uh, it seemed like there was some repeated structure that I wanted to try to isolate out. And by doing so, we actually get to write a few little bits of Rust that might be generally interesting to people. Sort of show you how to write a method that takes a closure as an argument as a way to tidy up some stuff. We're also going to try to respond to a very sensible complaint that the way the Sudoku reasoning is structured, it makes if you've not seen the previous videos, I recommend those first. This isn't the right place to sort of hop in midstream, but the process works by iteratively applying various rules to a board state, where we rule out more and more possible value row column combinations. But the way it does this actually is sort of in sequence, going through a bunch of things. We start with some determined values. From those determined values, we get some new candidates for the next time around. But then we use those and we apply some more inferencing, and finally we update all those candidates. And the thing that's annoying here is that there's some rules that are applied in sequence, which means that round by round we might take relatively larger steps than we can, as humans, can keep in our brain. And I'm going to try to restructure this a little bit so that in each round, all of the facts that we derive are consequences of facts from the previous round, not any facts from the current round. And hopefully that'll make it a little easier for us to piece together why we were able to reach some conclusion in a particular round. We should be able to just look at the facts in the previous one, and it should be relatively immediate. The application of one of the rules that we've written down. So let's start with a thing that I hope is going to work out, but there's a lot of repeated structure, and we're just going to look at this little bit of code here to see it. A lot of repeated structure. There are 4 places in the code where we apply roughly the same logic over and over again, which is we take our board state, which is triples val, row, and column, meaning that the value could possibly exist at this row and column location. As there are fewer and fewer of these, we get more certain about the value at a particular location. In particular, if it ends up that there's exactly one value at a particular row or column, that's pretty exciting. We should pay attention to that row and column and lock it in, basically. And the way that we do that is we fish out from these triples some key, this row and column. And we keep those key values that have a count of exactly 1, and anything that doesn't have a 1, like it has a 2 or a 3, we essentially get rid of it. We set its count to 0, which is the equivalent of discarding it. And then with those keys, we return back to our original board state, and we go and do what's a semi-join, which essentially says, keep those entries, row and column, for which which happen to map to the row and column. So val, row, and column. If this row and column exist in our determined set, just keep that triple val, row, and col. Though we write it in some weird row, col, val sort of way. Oof. All right. Well, that sounded like that might have been pretty specialized logic, but in fact, a bit further down in the code, we're similarly interested in these triples situations where there's a single val row. So if there's of course each value in Sudoku needs to occur in each row, and if we look at all possible places a value could be in a row, and it turns out that ignoring the column, that there's only one of those, that's got to be the location. And when we find it, we want to go and fish it back out, and that's all of this logic is essentially doing the same thing, where instead of looking at row and column, we look at val and row. And the goal is still the same: fish out the corresponding column. We do the same thing with columns down below. Exact same type of reasoning. If there's a value in a column, since each value must exist in each column, if there's a value in a column where there's only one row, down here, over here, one occurrence of it, then we'd really want to fish out that value in column, figure out what row it was attached to it. So that looks very similar also. And the crazy one, we're going to try to make sure we're general enough to accommodate this too, is this the same logic but for these 3x3 cells. So for each val, row, and column, this maps to a cell. Essentially, we could take the row and column and divide each by 3 if we wanted to. That would give us a key, essentially, that tells us what cell we're in. And if there was a cell that had a particular, just a count of 1 for the associated value, we should go fish out the row, column, val associated with that cell. And that's a bit more gross. That's a little, it's not exactly the same pattern over and over again, but I think we're going to be able to accommodate it. And we're going to hopefully clean up all of this filthy logic and sort of turn it into about, not exactly 3 lines, because we're still going to have to write this at least once, but something a lot more compact. So let's try to write that. We're going to start with a signature, which is going to be similar. I just want to steal this because it's easy to get all of our various of our generic parameters tidied up. We'll drop down here and pop this down, and we're gonna let's say call it keep unique. Which is going to take a few things as inputs. So we're gonna have it take in, for sure, a whole bunch of these value, row, column triples. We're gonna have it produce a whole bunch of value, row, column triples. That's gonna be our intended contract, is candidates that come in and those folks that are unique in whatever sense we're looking for. But we have to figure out some way to describe how they're unique. So in the very first instance, we picked out the row and column fields. Then we picked out val and row, then val and column. And then we picked out some weird val and cell sort of thing. And one way to do this in Rust is to write these nice little generic methods where they take generic parameters. I'm going to say f for function. And we're going to be able to write something like some logic that is going to be of type f. You might say that's not super helpful. What is f? And we have the privilege now down here of adding in some additional constraints. So we've already imposed a constraint from times ago where the G type here associated with our collection, this is the timely Dataflow execution scope, has to have some properties. We can just add another one that talks about our function f. So will f be a, I'm thinking of it as just a function. It's going to be a function, let's say from I8, So reference to a I8 triple, I guess it doesn't have to be a reference because it's a copy, but let's just do that. And it's going to go to, if I can find there we go. Something. Well, we don't really know what it's going to go to. Like in some cases, it was just a pair of integers, right? But actually in that cell case, it's going to be it was row call, val row, val call. But in the cell case, actually, it's something weirder, right? It's like a pair of a value and these cell locations, which are also pairs of integers. And we could try to jam that all into a pair of integers if we wanted, but we can actually just make this a bit more generic. So we'll let it go to some function d that we'll also add as a generic parameter, d. And d is going to need to have some constraints as well. Let's not type them yet. Let's just start writing our program, and we will figure out what we're going to need to add for d constraints. Basically, differential data flow is going to need d to have some properties like the ability to test for equality and having a static lifetime so that we can move it between threads in principle, stuff like that. But let's write our little fragment first. So what do we have? We have a collection start, and we've got this logic thing that we can apply to each of these elements, which sounds I don't know, I think sounds like a pretty good start. So let's go from start. I'm going to hit this with a map function that has our triple here, and I think we're going to want to produce two things. Do we want to produce two things, or do we just want to? Let's just produce one thing actually for the moment, because we're gonna. If you recall up above, we start from our thing and we produce just the keys first, because we want to go and find the unique keys. We haven't actually gotten around to doing our semi-join yet. So for the moment, actually, we're just going to do logic applied to trip. This is going to give us the set of keys out there. We're really interested in those unique ones, so we're going to write, again, that threshold logic, which took, well, let me just sort of copy however it worked. Has a value, you know, a key that we're not really interested in, and a count. So we'll just steal this. And I suppose we should try to make this a bit more readable. So we have some key. We don't really care what the key is. Or I should say, the specific value of the key is not going to be important for us. So we're going to let these be the unique keys. And this is great. This is essentially what we did up above when our logic selector picked out row and column, row and val, or val and column. And that's also what we did with that cell stuff that was totally unreadable. So there's no reason you should have been able to see that common pattern. And now what we're going to do is we're going to apply our previous idiom up above, which was to take start and again hit it with a map. This time we're not going to look at our trip. We're not going to discard the payload, so we're going to do logic of trip. But then we're going to keep the triple also, because we want to retain the full data. Like if we're going from val row call to just row and call, we'll need to get the val back somehow, and we're just going to keep it there. We're going to keep actually the whole triple. So we're going to semi-join with the unique keys, and now we're going to map, so that will retain all of these pairs of a key and a triple that were found to be unique. And we just want to get rid of the key now. So we have a key and a trip. We'll just turn it into a trip. And this is a method now. I think we're missing some constraints. So we're missing the constraint on D, which is going to need to be some more things for this all to work out. But we can check out what's going on over here. If I can. All right. So we've got some constraints here. So let's look at a few of them. So D, whatever this type D is, doesn't implement clone. That's true. In fact, there's lots of things it doesn't implement. We could let it be clone, but actually it's going to turn out that for threshold to work, the reason we can't find a threshold is because threshold's only defined for types that implement certain differential data flow idioms. So let's put this in, and I'm going to use the trait that differential data flow is almost certainly expecting. Could go and double check that, but turns out there are a few traits, all with the same name. All right. Now, this threshold still is not found, and this is probably because we need to be a bit more particular. I think the data is almost certainly, we could check, almost certainly good enough for us to move data around, but we probably also need it to be hashable. So because we're going to need, in our threshold logic here, to distribute the data around by the key, we need this to be something that we can actually go and shuffle. Let's go and check. So if we check out threshold, we can check that K has to be exchange data, which is also something in differential data flow. Let's try that out and see if that. Exchange data are can't be the only thing though, I don't think. Possibly. Well, okay. Let's see what happens here. Exchange data are things that are allowed to be shuffled around. Yeah, we gotta do a little bit more work. This is one of these exciting Rust moments where you get to try to track down what exactly. Yes, good. So we also want the hashable trait. This is the thing that lets differential data flow crack into it and gets like a hash value out so that it can hash distribute between various workers. And this is totally fine. We just throw that down in there. And it's going to turn out this is totally fine because the only Ds we end up picking are just various combinations of integers. Oh, this is not... oh, yeah, right. Sorry, we're not in the differential data flow crate, so we have to go and explicitly call out where to find it. It's getting wordy enough that perhaps we should include these things somewhere else. All right, we've got a few more complaints now. These are legitimate complaints. So Rust is complaining. You can see over here that the type parameter f may not live long enough. We haven't insisted that f be anything other than a function, and it could be a function that borrows some data or something like that, and that's not acceptable because we're going to try to jam that function into a differential data flow operator, which is going to get shipped off, go do a bunch of things. This is totally fine. Also, this is again just a throw a static constraint on there, and all that static does is say that in terms of lifetimes at least, f should not contain anything that can't live at least as long as static. So own data is fine, and static references are fine. Borrowed references of shorter lifetimes are not okay. All right, getting some more complaints here, and these are of the form, various closures don't. They would try to borrow logic. We can't have that. We need to actually take ownership of it. It's going to be a little complicated. You can sort of see because we're going to use this twice here, which, we could do this a few different ways. We could make f also implement the clone trait, which is totally legit. We could, let's actually do this slightly differently just to keep things a little simpler than that. We'll have a keyed relation, which is going to be start.map of move of trip to so this is just going to be a pair of the key and the associated value, and then the unique keys are going to be keyed.map of key and don't care to key, followed by the threshold. So this is it's a little gross to read, but is taking the exact same pile of data and just keeping the key. And now we don't have to call this second time. We can just say keyed. And now we've only actually used logic once. We're, instead of cloning the logic that we're using, we're cloning the data. It's probably less efficient actually, but this is meant to be a little easier to understand. And great. So that looks great. We're being warned that we don't actually use the key down here. That's a good point. I am a big fan of fixing those sorts of things up because if you, the human, doesn't agree that that's supposed to be unused, there's probably a bug, so worth fixing. So we've got our keep unique function now, which keeps the things that are unique by a thing. Let's call it by. Just to remind ourselves that it's only unique with respect to some particular closure. And let's try to rewrite some of our logic up here. So determine, for example, I'm going to say, hopefully is keep unique by. Did we give a reference? We did give a reference. Board, and we're going to give it a closure now of triple. So v, r, c is going to go to r, c. And we have this little printy thing there. So let's keep that. But this is what the code looks like now. with the probable correction that we want to underscore the value there because we're not actually using it. Let's see what happens here. No. Is this okay? Sorry, this is quite possibly because yes, great. We're expecting a different structure over here now. So we actually return value row column. We all of our uses of determine now. We're pretty sure that we left it in this row column val format, which we can fix up. I mean, I think we should fix up. What happens if we just mass replace all of these things by yeah. Oh, this is gonna work out great. Maybe. Let's go and just mass replace all of them by val comma row comma call. And some things are now kind of silly, like this is obviously a not very useful function. Let's get rid of that. We'll have to double check. Like I guess this was all totally fine. That was just moving random shapes around. We don't need that at all. And let's see if this is any happier now. Good, right? Okay, sorry. So the problem now is that we have taken a reference to some triples and produced things R and C that are actually references to rows and columns. So let's tidy this up. I think this should work. This is how I would normally write this code. You can cat a reference to a. It's a little surprising that this is such a big complaint. Right. Okay. Sorry. The problem isn't the reference here. Actually, it's the shape. It was thinking again that we wanted these row call pairs. So we want to be a little careful here because I think all of these exclusions are actually shaped as row call val things rather than val row call. But why don't we fix that up too while we're here? How many parens do we have? Doesn't look like enough, does it? And we're going to do some stuff down here, same sort of thing. Looks good. This one doesn't actually end with a... okay, so we're going to need to change a few points here. Looks good. Oh, this is gonna be a bother. That's terrible. This is my mistake. Let's just do a little bit of nonsense down here, and we'll feel bad later. Great. Now this is more probably correct. I hope. Great. No method anti-join. Yeah, okay. This makes some sense actually. The thing that we were doing down here in terms of moving the shapes around was actually useful. It was a bit it was inappropriate to go and remove that on account of, I mean, when we did the textual substitution it made sense to remove it, but to do an anti-join we actually have to have the data in the keyed by row and column. So let's put that back in. So this is going to be a map from to row call val, and having, let's see, the locks things are going to be what shape do they have? val row call. Okay, great. So we're going to need to, before we concatenate in the locked values, we're going to need to map things back. And we're just going to put that back as val row call. Great. So that compiles. Let's run it and make sure that it at least does a related thing. And all of that work, let us go and type this first line much more concisely. So while this is compiling, we'll admire what we've done. We have this method keepUniqueBy that takes in the board and just a little closure that tells us the keys we want to use. And we get out, again, vals, rows, and calls without all of the horrible semi-join stuff. I mean, we've written that down below, but we're gonna be able to reuse it. This looks promising. Who even knows? These are now, actually the output is different now because it's, instead of being row call vals, it's val row call. So we have a bunch of 1s and 2s at various locations in the board. They look to be the same set. We had 7 of the rows completely determined with 1s and 2s, and 2 of them, the top and bottom, not determined at all. So let's clean up the these other instances of this method. So val row, if you might recall, took candidates in this case and reduced them down. We're going to do candidates for now, but we're hopefully going to change this to be board at the end. Just that was our second task, was to try to simplify the reasoning. But let's do something, keepUniqueBy candidates. And our closure that was going to go from VRC to something is going to go to, we need to make sure to fix the referencing there, V, R. And actually that's going to end up as our row lock. So these, the val rows were the values in rows that had just a single bit of support, and then we did a bunch of other work to fish out the original things. This is just row lock from down here, though, and we can delete this whole pile of code. Same thing with presume call lock, which is going to be keepUniqueBy candidates. We'll take again reference to V, and R, and a C, and this time we're going to use V and C. So the value in the column, if there's a unique row that represents it, we're going to keep that value row and column triple. Let's make sure this, before I go and make a horrible mess of the next section, let's make sure that this is, it's compiling at least. I'll just drop that out there. I'll drop this out here. And the thing we're going to need to do next is basically, this is going to be our key. This horrible mess. Though fortunately, we're only going to need to type it once now. So let's get that ready. So that's going to be keepUniqueBy candidates, and now we write our little closure thing, which is going to be this this mess here. And this definitely is a little bit of a mess. It would be a little bit simpler if things were started at 0 rather than at 1. We could just divide by 3. So instead we're like futzing around with these things and dividing by, subtracting 1, then dividing by 3. And we're scaling back up again. We don't really use that, do we? I think we must have stolen some code from somewhere. But this is now our little bit of logic. And this is cell lock. And we're able to go and delete all of this stuff, I think. So let's check this out. That's exciting. Can't find, oh yeah, sorry. So it's now R and C. And we're going to keep the So importantly, right? So the key is going to be not just V and R or C, but V and this weird composite thing that, again, we could have made an integer if we really wanted to, but the intent of this is a bit clearer, if such as it can be. All right, and now like our locking code down here, the stuff that says if there's only a single representative from a particular region, row, column, or cell, it's a lot simpler, right? Like this is, a bit more concise. We're getting the same results, which is good to see. Great. And all that it took was writing this horrible mess, which, admittedly has a bunch of crazy symbols in it. We had to write a bunch of trait constraints and stuff like that. Though, hopefully by doing this, we agree that we sort of teased out a recurring bit of logic where we want to reduce down some collection of possibilities by some piece of some identifying key. And now, when we try to reason about what's going on up here, this is a fair bit simpler. Still a whole bunch of horrible stuff, but these moments that also used to be more complicated are now simpler. All right. Well, that was good. Let's applaud ourselves for that actually having worked out. I hadn't tried this ahead of time. I'm glad that it did. So the next thing to try to do is to try to write this logic in a way that each of the bits of inferencing that we do starts from board and doesn't use anything else. It doesn't rely on any other bits of inferencing done throughout the loop. And in particular, we're going to want to sort of move this logic a little bit lower and have these folks be determined by board, not by candidates. What that's going to mean is that these locking bits of logic shouldn't see the consequences of having done any exclusions yet, because that just makes it a little hard to track down. When we see two outputs over here on the right-hand side, for example, in the same iteration, iteration 4, one of them could derive from the other. We don't really know which one comes first. It's just a little awkward. So actually, let's steal this so that we can consult it later. Maybe something will change. Maybe nothing will change. But we'll come back to it. Get rid of threshold. So what we're going to do is we're going to think about deferring this logic for a little bit. Actually, let's cut it out. This way we won't screw that up. I'm going to put it down here. We'll have to stitch things together a bit more carefully. But we're going to change these candidates to be board, and board. So now each of these bits of locking are determined by the initial state in this iteration of the game board. And we now have a whole pile of bits of information that we've assembled. And we want to put them all together. We've got a bunch of exclusions. We've got a bunch of locking things. Hopefully they don't conflict. And we have our initial board state. We don't even necessarily have any candidates yet. We're going to be defining that here. So we have board. We've got our various things that we want to delete. And I think, to be honest, we could just chain all these things together. So if we just don't bother calling anything candidate, chain all this stuff together, and we'll delete that. I think. Yeah, good. This is now it's a little complicated, but what we're doing is assembling all of our exclusions, negating them, saying you don't belong on this board anywhere. And for what's left, this was this bit of logic is this weird logic. Weird, but like the stuff that says, hey, if you went negative or down to 0 negative or anything like that, you're dead to us. To deal with the fact that there might be multiple exclusions here. We could, I think in principle, get rid of this if we just did a distinct here. And maybe that's a bit more idiomatic. So we take all of our exclusions and say there's a lot of reasons we might throw someone away. Let's distinct them up. Actually, I take that back. There's a reason why we want this thing here. We could have done that in principle, except for the fact that with all of our weird extra new rules from these chess rules, the knight's moves and the king's moves, we are producing a bunch of constraints off the sides of the board, and our orthogonal constraints produce constraints on values like 0 and 10 that don't exist. So this threshold actually get tidy all of that up and make sure that we don't circulate some negative, like a -1 constraint for 10 or something like that around. So this is basically just tidy things up. Then we do our little anti-join trick where we say, for everything that came out of here, let's delete anything at all that shares a row and a column with a location that's supposed to be locked in. We then concatenate back in to lock it in. And we consolidate at the end to make sure that the thing we circulate around is reduced and anything that would have canceled actually goes to 0 and is not seen. That's an important part of making sure we terminate. So I'm hoping that we'll get something over here that is the same answer, but possibly with slightly different derivation. And we can check out and see, hopefully a bit slower derivation, really. Well, this is exciting. I mean, the answer does seem to be the same. Well, same number of accounts. Interestingly, it's rigged up so that it actually takes 2 rounds for the information to make its way through, not 1 round. I'm going to copy paste these things over here just so we can look at it and see. That's probably a bug, if so, or a bug, but like differential is rarely wrong, but we can definitely do stupid things. So it looks like we're seeing exactly the same thing. We've just taken twice as many rounds of iteration to do it. So when we learn a thing, we learn that thing in even rounds in this new version, and this is not impossible, in the sense that you look at the paths through here. If everything ultimately needs to determine from some exclusion rule, that will happen. That may not be what causes us to actually lock in the value. Locking the value might be the thing that causes us to finally get down to the conclusion, and maybe every derivation actually involves from some new change as to the things being determined. So the determinants flow into the exclusions. If an exclusion happens but does not inform the locking in, that is not unreasonable. Like, we're unlikely, let me say this a different way. We're unlikely at this point in the Sudoku game to determine the specific value of a location simply by excluding all of the alternatives, right? Like, we're only learning anything about 1s and 2s over here. We're not excluding 7s or 6s or anything like that. So in actual fact, maybe this was a premature action over here. In actual fact, it seems like the only time we actually learn a thing is due to these locking steps. And it appears that the locking steps, at least, this I guess also makes sense. The locking steps only create progress by exclusions. Right? The only reason we would come to reduce our options enough so that they get locked in is because other alternatives got excluded, right? So like a locking in of a particular, I suppose it's possible actually, but the locking in of a particular column value in a column, the only thing that that's doing is deleting options at that location, right? So if we lock in a value at a particular row and column, we don't go and apply any other exclusions afterwards. We could in principle, but so this leaves us with an interesting question, which is, or I think it's interesting, which is, what is the thought process that people's brains are actually following? Differential data flow, it seems, needs to take pairs of steps to actually perform various derivations. And what is a sane thing to do if we're trying to track how humans think about things? Do we look at the board and say, well, here are the unique locations, let me cross out a bunch of stuff, and then let me go and look at these locked in values? That's what we did the first time. And it was a little hard to follow, to be honest. Though I should also say that we didn't take great pains to confirm that we were failing to follow. We just sort of struggled to follow it. But I'm gonna leave this in now, because in principle, in the future, we might start to see various rules like exclusions determine values for us. We could probably see this if we let's for the moment, let's comment out the chess stuff. And let's put back in the tricky Sudoku puzzle, not tricky, sorry. The one we expect to solve. Sorry, definitely not the tricky one. And we should be able to run this again. And I'm optimistic that we'll see some odd numbers over there. Maybe. Oops. Comment this out everywhere, not just. Just a moment. While I discover which keys are the right ones to press. There we go. Not those. All right. So this is more fleshed out game board that we actually expect to solve, and we might imagine that we initially solved it actually just by applying the exclusions rule. We didn't even need to. Yeah. So there's definitely some odd numbered steps in here. It's good to see. A large number of the locations are determined because they're specified as part of the input. That's not especially stimulating. But fairly quickly, I guess we learned some things, presumably by way of exclusion, because the initial board state has some determined locations and some utterly undetermined locations, and I think there are no rows or cells that are all defined except for a single element. We have to start using some of the exclusion rules first. So this shows us, I suppose, that these derivations can actually happen in alternate rounds, and doesn't chain any of them together. So that's good. I'm relieved to see that this actually did a thing. It wasn't just multiplying by all the rounds by 2. But for the moment, let's put back in our complicated puzzle. There we go. And yeah, so this has just been tidying. You might notice, if you've been paying attention over here, that we haven't been solving the puzzle. There's some more bits of thinking that we're going to need to be able to do before we can solve the puzzle. Some more generalizations, essentially, of the rules that we've been doing. And I haven't entirely figured them out. I mean, I have my opinion about what these generalizations look like, and we're going to try to work through those when we have a little bit more time. They're not nearly as trivial as... they're generalizations of the exclusion rules, but sort of potentially interesting generalizations of them that don't need to only start from locations that are determined to be single values, but rather can start from sets of locations. We will see if that pans out the next time around. So for now, we're going to stop and have to think about how to take a bigger swing at this interesting and complicated problem. Thanks.